I want to talk about roaming. But I want to talk specifically about what we call fat secure roaming. So roaming, when we have an 802.1x association to an AP. That's what we're going to talk about. So before we talk about roaming from one BSS to another, one AP to another, I want to just review what happens in the 802.1x process. So when we associate to an AP, and we're using WPA Enterprise, and we're going through 802.1x, there's several steps we go through. The first of that is we go through what we call open system authentication. Open system authentication is one of the original 802.11 authentication methods from the Prime standard. And it's basically no authentication, but we have to go through authentication. Open system allows everyone on the network. In the original standard, there was two options. We could do open system or we could do shared key. Shared key confirmed we both had the same WEP key. And hopefully no one's using WEP today. So our other option was open system. We still have to do it today. So the first thing we do is we go through open system authentication. That is done with 2 packets. We send an open system request to the AP and we should get a successful response back. It should never fail. Following our authentication onto the network, we then have to go through association. Association is, again, a 2-packet process. We will send an association request, and we should receive back an association response frame from the network. At that point, we are what we would class as authenticated and associated to the AP. An association is logically equivalent to having a link light on a switch. I've plugged into a switch. I've got my little blinking light. I'm connected to that switch. In terms of Wi-Fi, when I'm associated, I'm connected to the AP. Now, just because I've connected to the AP doesn't mean that that AP won't prevent me from passing traffic till I've gone from some further network authentication, some back-end authentication, just like a wired switch does. If I'm wired into a switch, it may prevent me from pushing traffic on the network till I've gone through some further authentication. And that's where we get our 802.1x authentication, where we would authenticate with a radiate server, and we get some EAP packets, which is our authentication method, and we go through the 802.1x authentication. If we are successfully 802.1x authentication, that's my section in purple, we're then going to go to what we call the 4-way handshake, which are these EPOL key packets in green on the slide. And this is where we exchange our security keys that we're actually going to use to encrypt our data transfer. So that's our process we go through. 802.11 authentication, association, we've got an 802.1x exchange, and we've got this 4-way handshake. One of the issues with this process is it can take quite some time, particularly the 802.1x part. Depending on where your radiate server is, it could be at a centralized location, you're at a remote site, you may be doing that 802.1x over a WAN connection. So it can easily take 200 milliseconds or longer to do an 802.1x authentication onto the network. And for people who know what voice requires, we generally say with voice, we don't want to have any delays more than 150 milliseconds because anything longer than that is audible to the user. So this whole process can take a long time. And let's have a look at what happens with this process when we move from one AP to another. I'm going to call it a slow roam. Without any sort of mechanisms to help us roam from one AP to another, this is how roaming will work. When we connect to the first AP, our initial connection to the network, we're going to go through open system authentication. We're going to go through 802.11 association. We're going to go through the 802.1x authentication process, that EAP exchange, and then we're going to do our 4-way handshake. We are now connected to AP1, and we can start pushing data. But what happens is our station starts to roam away from AP1 all the way to AP2. And as it's getting closer to AP2, it decides the signal strength for AP1 is below its roaming threshold. It's discovered AP2 is a better AP to connect to, and it will roam to AP2. When it roams to AP2, it's going to go through the same process. It will do open system authentication, 802.11 association, but this time it does a reassociation because it's moving from one AP to another AP. And part of that process in that reassociation request frame is the client is going to say, hey, to AP2, I was connected to AP1. So it includes the MAC address of the AP it was included to. That's one of the main differences between an association frame and a reassociation frame. What AP2 does with that information isn't specified in the standard. It's left completely up to the vendor to do something with that information or not. What we hope it'll do is it'll talk to AP1 and say, hey, if you've got any packets buffered for this client, they're associated to me, now send them over. And we can do what we call seamless roaming, where we don't lose any data connection. Because without that, doing this roam is like unplugging from one switch, plugging into another. You sever your connection when you move from one AP to another. So we hope that the APs or the wireless infrastructure, if it is a controller, is going to hand off my data connections in a seamless way. But one of the difficulties in this process is the amount of time it takes me to reassociate and go through this 802.1x process. There's also various other issues around roaming in case of when does an AP client roam? How does it decide which AP to roam to? If you come on an ECSC design course, it's what we talk about, the green diamond, the decision a client has to make. I'm not going to cover all that decision-making process. I want to mainly talk about today this process of once we've decided which AP to connect to, how do we do it? And as I say, one of the main problems is it's 802.1x authentication. It takes a long time. So if I want to roam quickly, that's going to slow me down. So what do we do about it? Well, the 802.11 standard has now defined something called 802.11r, which is a fat secure roaming amendment. I'm going to talk about that in a little bit, but before we get to 802.11r, I want to talk about 3 methods, industry-adopted methods, not standard-based methods, and we're never defining the standard, but adopted by the industry, that came out before 802.11r and are still used in lots of networks today. So we're going to see what 3 solutions to this problem, and then we'll look at what 802.11r defines. So the first of these methods is what we call PMK Caching, pairwise master key caching, also known as fast roamback, and you'll see why in a little bit. Let me tell you how it works. We associate to AP1. The client goes through open system authentication, it goes through association, it does its 802.1x, and it does its 4-way handshake. We are associated to the first AP. When we come to move to AP2, we have to go through the same process. We have to go through open system authentication. This time we go through reassociation, request and response. We then go through an 802.1x, and we go through the 4-way handshake. However, because we've been associated to AP1, one of the main things you do when you generate an 802.1x exchange is resulting from that, you get something which we call the pairwise master key. That is the key we need to feed the 4-way handshake to get all our encryption keys. It's the key that says you have authenticated to the network. So we cache that key. We say for AP1, I am going to cache the pairwise master key, the result of that 802.1x authentication. And the AP also caches it as well. So now the client and the AP both have a cached pairwise master key. If the client should then decide to roam back towards AP1, when it roams back, it goes through open system authentication, and then this time in the reassociation request frame, it says, hey, I've got a cached pairwise master key for you, can I use it? And the AP will go, yep, we can use that, and then it can go straight to the four-way handshake and miss out the 802.1x exchange. So this process now negates us having to do a full 802.1x if we roam back to an AP we've previously been authenticated to. You'll see this in, this is the robust security network information element you get inside reassociation request frame. And one of the things you can see here, if we use a little pointer, is you should be able to see the PMK ID. This is an ID of the cached pairwise master key. And this is a client saying, hey, I've got a cached pairwise master key for you. Let's go straight to the four-way handshake. So that's quite good. The problem with it is I can only use it when I'm moving back to an AP I've previously been authenticated to. And if I'm walking one direction through my organization, I'm never going to roam back to an AP I've previously been authenticated to. So a sort of enhancement to pairwise master key caching, which builds on top of pairwise master key caching, is something called PreAuthentication. This is how PreAuthentication works. When we first associate, just like with all the other methods, we have to do open system authentication, association, 802.1x, four-way handshake. And we cache the pairwise master key. This time, as the client is roaming towards AP2, it goes, hey, AP2's over there. That might be an AP I want to associate to. I've identified it as a candidate AP I may roam to. So while it's connected to AP1, it does an 802.1x authentication with the candidate AP prior to roaming. So it sends all the packets through AP1 to AP2. What does that allow it to do? It allows it to cache this pairwise master key for AP2. So then when it comes to roam, it can just do open system authentication, reassociation, hey, I've got a cached pairwise master key for you, four-way handshake, we're on the new AP. Even though we've not been associated with it before, we've pre-authenticated to it over the wire. And again, if we're looking in frames, you'll see there's support in the robust secure network information element. It will have a little flag, which we can see down here, which says supports pre-authentication. Again, that needs to be supported by the client and the AP vendor to do this. Both of these two methods, pairwise master key caching and pre-authentication, will work with any sort of vendor solution, controller-led solutions or controller-based solutions. But there was a thinking in the industry around when these methods were coming out that most solutions had a controller. And if we've got a controller, can we be more efficient? And that's where a standardized method called opportunistic key caching came from. And opportunistic key caching works a little bit like this. Open system authentication, association, 802.1x, four-way handshake. But notice this time we're associating with the controller, not the AP. What that means is we've actually authenticated with the controller, and now it has a cached pairwise master key. And so does the AP. What that allows the controller to do is to then pass on this cached pairwise master key to APs I may roam to, or some of them just pass it out to every AP within a mobility sort of domain. When I then roam to AP2, we go through open system authentication, reassociation, hey, I've got a cached pairwise master key, and we can go straight to the four-way handshake. So it's another way of negating that use. Some people might also know there's a Cisco proprietary method of this, and this actually negates the use of needing to do the four-way handshake as well. But we're not going to go over that in this section. So they're the three, what I would call pre-802.11r ways of doing fat secure roaming. And their whole purpose was to try and remove the need to do the 802.1x authentication every time you roam to a new AP. But none of these were defined in the 802.11 standard. And an amendment called 802.11r was the IEEE's preferred method to standardize these processes. So let's have a look what 802.11r does. 802.11r is one of my favorite 802.11 amendments. Don't know how many people here have a favorite. Many? Okay, maybe it's just me. This is probably my favorite, so there you go. I'm not going to go through all the complexity on this slide. I want to go merely to how it works. But the theory is you have a wireless LAN controller or some device which is central to that mobility domain, I guess, really. So it could, if it's a controller-less environment, it'll probably be one of the APs designated as the manager. But they become what they call the pairwise master key R0 holder. They are the device which holds the master key, which you get when you first associate. And from there, it's going to push keys out to the other APs. So a little bit like opportunistic key caching, which we've just looked at. Now, there's two methods for doing 802.11r. There's something called over the air and over the DS. And I'm going to explain how both methods work to you. And then maybe we can just talk a little bit about them once we've talked about how they work. So let's first of all talk about over the air. Romanization, initially it needs to associate to the first AP. So it goes through open system authentication, association, 802.1x authentication, a four-way handshake. Your initial connection to the network still hasn't changed in any of these methods. We have to go through the full process. But again, we're authenticating with this centralized device who can become the pairwise master key, what we call the R1 holder. They can then send copies of that key to all the other APs. And the client and the controller both have the same algorithm for generating these cached keys for APs. So they can now both generate the same cached keys, which is when we roam, we can do it a bit quicker. But here is where it differs from all the methods I've shown you so far. And this is why I like 802.11r. Look what happens. We don't do open system authentication anymore. 802.11r introduced a new authentication method, something called FT authentication. It's still 2 frames. Can I do FT authentication? Yes, you can. Then we do a reassociation request frame, we get a reassociation response. And that's it. Really, really efficient. What's happened to the four-way handshake? It's gone, hasn't it? Well, what's really cool about 802.11r and FT fast transition is it embeds the four-way handshake into these 4 frames. That's why we have a new authentication method. All the packets from the four-way handshake, all that data that gets exchanged is now embedded into these 4 packets. So instead of having 8 packets, we only have 2. And this means the roaming time is significantly better. So if we just compare pre-802.11r fat secure roaming methods, they were all about, let's get rid of the 802.1x. So when we did a roam, it was open system authentication, reassociation request response, then the 4-way handshake, the 4 key packets. With 802.11r, we've got auth, request, success, reassociation request response, and the 4-way handshake is embedded into that process. Now, without going into too much detail, I thought I would show you those 4 packets. I appreciate we're not really gone over what happens in the four-way handshake, but for the people who know what happens, I'll just show you a few bits of information that's interesting in these packets. So here's the first one. It's the FATS BSS transition request from the client. And inside here, there's an information element called the FATS BSS transition. And here is where all the four-way handshake stuff is happening. So one of the first things that happens in a four-way handshake is the supplicant, which is the client, and the authenticator, the AP, they exchange nonces, which is just a random number they generate. And we see in this first packet, the S nonce, the supplicant nonce, is being sent. That's the first part of the four-way handshake. The next packet, again, down here, we now see there's an A nonce and an S nonce. They've now successfully exchanged these nonces. When we look at packet number 3 is now the reassociation request frame. So we've had the 2 authentication frames. Now we're inside a reassociation request frame. It also has its FATS BSS transition element. And now there's some more information in here. There's something called a MIC, a message integrity check, which is a way of them sort of confirming that they've both generated the same, what we call the pairwise transient key, which is just a key we use to encrypt data. But it can also use it to generate a MIC. So they've exchanged nonces, they've generated a key, and now they can say, hey, this is my MIC, so you can confirm I've got the same key. And they both exchange MICs. So we see a MIC in this packet. In the next one, it's a bit bigger, because this has the authenticator MIC in here, which is up here, but it also includes a key. And this is what we call the group temporal key. It's a key that the access point uses to encrypt broadcast and multicast traffic. And it's got to send it to the client. So it encrypts it in the key they've just negotiated and sends it in the last four-way handshake packet. So that is our over-the-air. Let's have a quick look at over the DS and see how that works. Initial connection, open system authentication, association, 802.1x, four-way handshake. The controller passes out the pairwise master keys, all the same as before. But this time, as the client's roaming, it goes, hey, I want to roam to AP2. So instead of roaming directly to it, the first thing I'm going to do is I'm going to send my FT authentication via AP1 to AP2. It does this in 2 action frames. So when it comes to actually roam and leave AP1, it just needs to do an association request, association response, 2 packets, and we're on the network. So this is just a quick summary of that process. That is fast, secure roaming. But there's a couple of other amendments to do with roaming I want to quickly cover in the last few minutes of this presentation. One of those is 802.11k. 802.11k was all about, okay, now we've made this roaming time quicker with R, but remember that little green diamond I talked about? Can we make clients make better roaming decisions? Because one of the problems is that clients roams over here, and it goes, yeah, I'm happy on that AP. Yeah, I'm happy with that AP. Yeah, I'm communicating with it at like MCS1, but I'm happy with that AP. And there's a better AP to connect to. So can we make clients make better roaming decisions? 802.11k allows the client to request from the current AP, hey, is there any better APs I could be on? Okay, and it does that using something called neighbor reports and neighbor requests. Let's have a look at how it works. Here's a station. It's connected to AP1, and it sends what we call a neighbor request. Hey, is there any APs around that I could connect to? And AP1 will generally communicate with the controller or the rest of the wireless infrastructure, and it will come back and go, hey, these APs would be good APs for you to connect to and roam to. So it gets a list of APs. Why is that useful? Well, if I get a list of, say, 3 APs I could roam to, then when I'm getting to a point where I'm dropped below my roaming threshold, what would a client normally do? Go off channel, start scanning channel 1, 2, 3, and right through all the channels, finding what APs are to connect to. But now it's got a list, so it can just scan and probe on those 3 channels, and it can quickly find out about a better AP and make a quicker, better informed decision. And it's not having to do so much off-channel scanning. In fact, if it completely trusts the AP, it could just go onto that one channel of the AP it picks and probe and connect on that channel. So it can make quicker roaming decisions. This is what a roaming request looks like. You can see it saying, hey, I'm requesting neighbours for the SSID blue. And then this is what the neighbour reports look like. Again, we won't go through all the detail, but you can see channel number is one of those bits of information. It gets told about its neighbours. One other amendment that's designed to help roaming is 802.11v. Now, 802.11k is all about the client initiating everything. Hey, can you tell me about my neighbours? Okay, thanks for the report. Now let me make a decision. 802.11v uses neighbour reports as well, but now it's about the infrastructure saying, hey, go and connect to this AP. I'm in charge, not you anymore, client. That's what V is really all about. This is how V works. It does something which we call BSS transition. It wants to transition you from one AP to another. And it can do that by sending an action frame called a transition management request frame. And we'll have a look at what one of those is in a minute. And that contains a list of all the target APs, all the target BSSs it thinks you should connect to. Hey, you shouldn't be connected to me anymore. You're better off connected to one of these APs. The station, though, can then send a response. Yeah, OK, I'll do that. Or, no, I'm going to reject it. And then if it does accept it, hopefully it will move. I just want to have a quick look at a couple of things in this packet now. Sounds harmful enough. But let's have a look at just one of these things here. Disassociation inament. That says, hey, these are some good APs to connect to, and this is the number of target beacon transmission times, so the number of beacons you've got before I'm going to disassociate you. So I'm going to give you some time to move, but if you don't move, I'm going to kick you off anyway. It's not quite as friendly anymore, is it? Hey, go onto these APs, and by the way, within one beacon, I'm going to kick you off. It's a little bit more aggressive. And that's just showing you the response. So because we're short for time, I just want to get onto this last slide. So what about the 3 amendments we talked about? R, K, and V. Which ones should you use? What's a good idea? What's a bad idea? Well, I think to try and help answer that, I'll talk about an experience I had once when with actually some friends of mine in this room today, actually. We tried testing some of these things on a network we had just deployed. This was a network which had a requirement for voice roaming, and we had already tuned the client and got it roaming round its office building. And it was roaming well. So the roaming was pretty good. 802.11r was turned on. It was helping to negate all the 802.1x. And you could maintain a voice call as you walked around the office. So we were starting from a pretty good point. But we wanted to know what would be the effect of turning on K. What would be the effect of turning on V? So the first one we did was turn on 802.11k. Now, the test we were doing was we were doing some packet capture so we could actually see what was happening. We had a voice call between someone in a conference room and someone walking around the office. And we also had on the laptop a ping going to the default gateway or the wireless controller, I can't remember what it was, but to something on the infrastructure. Now, before we turned it on, with just R on, the voice call didn't drop, it sounded good, but you could see every time the client roamed because you saw longer ping times. There was a couple of pings with longer ping times. As it went off-channel to do its off-channel scanning, you noticed when it roamed. When we turned on 802.11k, same test, still good performance, but you could barely tell when the client roamed from the pings. We had massively reduced those longer ping times because now the client was being informed which channels to go to, so it wasn't having to go off-channel all the time and do all these long off-channel scans. It was just moving to the channels where the APs from the AP lists were and scanning on those. So K seemed to be a good thing. We then enabled 802.11v, did the test again. This time the voice call dropped. We lost pings every time we roamed. And the experience was quite bad, if we're going to be honest. And I think some of that was because the client didn't like receiving this request, hey, roam, and it was like, oh, I'm not ready to roam, okay, let me go off, let me try and scan, and it threw the clients into a bit of a panic. I'm also giving you a time period where I'm saying you've got to roam. It can use all the algorithms that's been designed in the Intel drivers or whichever client you're using. You're enforcing it into a decision, and it was therefore taking it longer to roam. So we disabled V in the end. Does that mean you should never enable V? This was one particular vendor on one particular code with a particular client. What I would say with any of these mechanisms, you need to test them yourself before you implement them. Test them. Make sure they work in your environment. But that's just a little bit of experience. That is pretty much the end of my session. But I do want to just spend a couple more minutes chatting to you about something completely different, if that's okay, which is something called the Wireless LAN Association. I don't know how many people have heard of the Wireless LAN Association or even members of the Wireless LAN Association. But just very quickly, the Wireless LAN Association is an association of wireless LAN professionals. So people like you guys in this room. It is a global organization set up to try and further the wireless LAN industry, to try and provide a voice for people who are installing, designing, configuring, managing, building wireless networks. There's a lot of people. There's a lot of voices in our industry, aren't there? There's a Wireless LAN Alliance. There is the IEEE. There is the vendors. There's lots of people who have a voice. And then there's lots of individuals who are trying to actually use the products and manufacture them. And it became clear that it'd be really great if we could have a united voice sometimes. And that was part of the reason for setting up the Wireless LAN Association. So what is it here to do? Well, it's here to support individuals. That might be helping you by teaming you up with a mentor, if maybe you're trying to go through some certification or you're new to the industry. It's also about growing a community though as well. What we want to do is we want to have put people in touch with other professionals. Sometimes you might be the only wireless LAN expert in your organization, and that can be a lonely place. Who do you go to when you want a bit of advice? Who do you go to? Have you got people you can contact? And that's so I'm going to talk about local chapters, which we have, and I'm going to talk about the UK chapter in a few minutes. The other thing the Wireless LAN Association is trying to do is create what we call documents or recommended practices. I'm sure we're at a Wireless LAN Design Day, so I presume most people here design good wireless networks. But how many times do you see wireless networks designed badly? Why are they designed badly? Because people are not following any sort of structured design methodology. They're not using tools like Akahau. They're not gathering the requirements. They're not doing a proper design stage. They're not validating the design. So what we want to do is we want to come up with some design framework standards which say this is a standardized way Wi-Fi should be designed and deployed. And then we can validate, hopefully, networks based off those standards. So we're also working on a series of standardized documentation as well. What about you guys in the room? Well, we have quite a thriving UK local chapter of the Wireless LAN Association, which is primarily headed up by Ellen Blake and myself in the UK. But we are, and what we've been doing is been running local events. Sometimes it's just a bit of a meet-up event where you can get to meet other people. Sometimes we ran, just over a month, we ran our very first actual training session, which was on wireless analysis. There's a picture from it, and it was really well received. So we're going to be running more events in the UK. So if you're not a member of the Wireless LAN Association, but you think, hey, it'd be great to go to some networking events, some training events that are sponsored and discounted, then do go on the website and join. It's I think it's $50 a year to be a member of the Wireless LAN Association. Our last training event was, I think you got £30 off if you were a member. So you don't need to attend many events before you start to get your $50 back. So I hope it's well worth you guys doing it. Just before I finish, one last thing to mention is we also have another way you can get in touch with people, you can ask questions, is we have a great UK Wireless LAN Pro Slack group. There is a link up here where you can self-register for this Slack group. Normally it's by, you have to email Nigel Burden, who set it up, but at the moment we've got a link just so we can get as many of you guys in the Slack group as well. So if you think, hey, I'd love to ask a CWE a question, or I'd love to ask someone a question, it's a great place to ask questions. So do follow that link. It is for our friends who have travelled internationally. It is for UK wireless people. I promised I would say that. So if you join and you're from the Netherlands, don't be offended if you get booted out. Because that will. It's not personal, but it is designed for, there is a Netherlands Slack group there as well. As there is, and there's also a general Wireless Pros Slack group which anyone can join. So there's lots of Slack groups, so this is the UK one. Thank you for your time. Thank you for listening.